Okay guys, so I'm recording the lecture video for virtual memory. So in the previous class, we briefly learned about the virtual memory. So first, you need to know the original purpose of the virtual memory. So as I mentioned, the old computer systems, the DRAM, so which means the main memory is was very expensive. So which means that we cannot use the very large memory. So problem is that the software engineers, so software programmers want to use the large memory, so without the limitation of the physical memory. So how can we solve this issue? As I mentioned, so actually in a computer system, so we can use the cache, right? So why do you use cache? The cache size is very small, but if we can store the frequently accessed data in the cache, then we can access this data very quickly. So, the main memory, like the RAM, is very fast compared to the storage systems. So actually in the old computer systems, we frequently use the hard disk drives, right? And the hard disk drives are very, very, very slow. So the idea is that we can use the main memory like a cache. So which means that the main memory size is very small, and then the storage size is very large. Okay. So, and then, the DRAM memory is very fast, but the storage is very slow. So, which means that to the software, the computer system provides the very large memory space, but this memory space is also located on the storage. Okay. So, but the frequently accessed data can be stored in the RAM. So when the load instruction, when the data is requested to this DRAM, then data can be fetched from the DRAM. If the request data is found in a DRAM, then this data can be fetched from the DRAM. But if the data is not found in the DRAM, which means that the request data is on the storage system, so then this data is transferred to the main memory, and then the data is transferred to the processor. That is the original purpose of virtual memory. But I mentioned that recently the size of the RAM is very large, but we are still use virtual memory concept. So it is because the operating system and then computer system provides the large virtual memory space to the software, right? But as I mentioned, we know on the same computer system, we run many processes concurrently. So which means that the many processes are running on our computer systems. And then, so actually our processes like applications access the independent memory space. So which means that actually our software wants to access the very large memory, and then this memory is also separated each other. So which means, as I mentioned, when we load the binary file, and then binary file also includes the load instructions, and then this load instruction access the data. But so because many processes are running concurrently on our computer systems, actually the DRAM memory spaces are shared by multiple processes. Okay. But problem is that the space of the DRAM should be dynamically allocated to each process. Okay. So what's the problem? The same address can be accessed by these different processes, right? But this address, but the data is different because so we are learning the different processes. So how can you separate these memory requests? So actually, even though the software access this memory space, but this memory space is the virtual memory space. And then when the software access the data on the virtual memory space, so actually this virtual address is translated into physical address. And then I said that the physical means in the computer system, which means it's real address in the physical memory, like DRAM. So actually using this physical address, then we can access the data. So which means if the different data is accessed by different processes, so which means that so we can access these different data using different physical addresses. Okay, so how can we manage these memory spaces in the physical memory? So actually the size of the physical memory, also the situation. So we don't know how many processes are running on our computer system. Actually, the hardware resources such as the memory space, and then also the cores, like these hardware resources are managed by operating system. So when the processes are launched on the computer system, then operating system also manages these learning processes. And then also operating system manage the hardware resources allocated to the running processes. So actually when a process is launched on our computer system, like process 1, so it's similar to the application. So if we launch a certain application, then this application may launch the multiple processes or single processes. So processes are very similar to the application. So when a process is launched in the computer system, then operating system provides the virtual memory space. And then this virtual memory space is very large, but it's fake space, fake memory space. And then this process execute instructions like binary instructions. And then when the binary, so for example, when the load instruction is executed, then this process execute this load instruction, but this address is the virtual address. So let us assume that this process is accessing this data in the virtual memory space. So in order to access the real data, then we need to know the physical address on the physical memory. So which means this virtual address need to be translated into the physical address. So these physical addresses are, so this process access the real data using the physical address. So we need the translation, the translation between virtual address to the physical address, right? So actually in a computer system, operating system, and then the processor hardware supports this virtual memory management. So which means that so it supports the address translation. Also it supports the some caching of the virtual memory translation. It's called the TLB. So but the original purpose of the virtual memory system is to use the physical memory like a cache. Okay, so this is the concept of the virtual memory. So as I mentioned, when a processor is launched on a computer system, then the virtual memory space is assigned to this processor. And then actually, think like this: when the load instruction is exercised, then we can just define the size of this address. So in this course, we are learning about the 32-bit computer systems. So which means that the address of this load instruction is the 32-bit. So which means what is the size of what is the maximum size of this computer system? Which means that the size of the memory space handled by this address. Because the address size is the 32-bit, and then I said the 1 bit of assigned or address is allocated the 1 byte size of the data. So which means 32-bit address can cover up to 2 to 32 byte. So this is the 4 gigabyte. So what does that mean? If the virtual address size is the 32-bit, then to the launched processor, computer system provides the 4 gigabyte of the virtual memory space. Okay, but this is the fake space, because I said the virtual means fake. Okay, it's a fantasy word. But to the software think that I can use this large virtual memory space, but it's not true. As I mentioned, with software access this virtual memory space using the virtual address. But when the software accesses some data on this virtual memory space, the real data can be found on physical memory or on storage devices. Okay, because the original purpose of the virtual memory system is to use physical memory like a cache. Okay, so this is the example. So I said when the load instruction is executed on our computer system, then actually our software access the data using a virtual address. Okay, so like let us assume that our process, so our application is executing load instruction, load A. So this is the address. So and then actually this is the virtual address. So which means that we can access the data using the virtual address A. Then if this virtual address is mapped into this physical memory space, and then it means that if our processor, so if our application access the data using this virtual address, but this data is found in main memory, so it's a physical memory, right? So what does it mean? So actually, so this virtual address is translated into the physical address, and then using this physical address, we can access the request data on physical memory, right? But we can imagine a different case. So which means, so let us assume that our application executes the load word B. So it's a different virtual address, but let us assume that this data is not found in the main memory. So this data is on disk. So it's a hard disk drive. So what does that mean? So software try to access the data using the virtual address B. Okay. Then we check this translation information. Okay. Then we can find this process can recognize that the requested data is not found in the physical memory, so physical DRAM, and then which means that we cannot find this data on DRAM. Okay, which means this data is on storage system. So what does that mean? So in this case, this event is called page fault. Okay, then the operating system needs to access the disk space, which means that the data structure on disk, and then this data is transferred to the physical memory, and then this data is transferred to the process. Okay, so this virtual address is translated into this newly allocated physical memory space, and then this data is transferred to the processor. This is how virtual memory works. So then what is required? When I explain how the virtual address is translated into the physical address, right? So the required operation is the virtual address translation into physical address. Okay, so which means the load word A is executed, and I said, this address is the virtual address. So in order to access the real data on the real physical memory, then this virtual address needs to be translated into the physical address. Okay, so which operation is required? So first, we need to translate this virtual address into physical address translation. So how can you translate? So actually, I said the virtual memory system is supported by operating system. So let us assume we can just translate the all virtual address. So for example, this is the virtual address 001. This is translated the 0, but physical address 0010000, and then 0x0002. It is translated to the 0x2001. And then 3 is translated to 30002. So what is the problem? So if every byte address is translated into the every byte of the physical address, then we need to know this every translation information for byte address. It's not efficient. Why? So how can you translate the virtual address to the physical address? So which means that it's like the mapping table. So which means if the virtual address is given to the mapping table, so it's a mapping table, then we can get the physical address. But if the every byte address is translated into the every byte of the physical address, then we need to require very large mapping table structure for this translation. So which means it's not efficient. So actually, we just translate the upper part of the virtual address. So which means this figure shows the address translation from virtual address field to the physical address. And then let us, in this example, the virtual address size is the 48-bit, okay? And then the physical address size is the 40-bit, okay? So, and then only the upper part of the virtual address. So in this example, address 47, address bit 47 to 12 bits are translated into the physical address number 39 to 12, okay? And this lower part, so it's called the page offset. This low part is not translated. This low part is just copied to the page offset field of the physical address. And then this is the size of this physical page offset is the 12-bit. So what does that mean? This page offset field occupies the 4 kilobyte of data. So which means when a virtual address is translated into the physical address, then we just translate the 4 kilobyte of data chunk. Okay, we do not translate the byte by byte translation. We just translate the upper part of the virtual address. So which means that this data chunk is the data chunk of the virtual memory space is translated into the data chunk of the physical memory space. And then this data chunk is a 4 kilobyte size of the data chunk is called the page. That's why this part is called the page offset. And then in this example, the size of one page is the 4 kilobyte. Okay, so this is how the virtual address is translated into the physical address. So let's see the example. Okay, so let's start here. So this is the example of the virtual address translation into physical address using the page table. So actually, this page table is the mapping table, okay? And then this mapping table is actually managed by operating system. So what does that mean? This page table is the software data structure, which means when a processor is launched on the computer system, then operating system will this page translation table allocated to the launched process. So it looks like the mapping table. So in like the A, how can I so like the M and then index, and then the output of this M is the physical address. So which means, so let us assume that load word is executing 0x. Load word is requesting data of virtual address 10004. Okay, so this is the virtual address. And then the page size is the 4 kilobyte. So let us assume that our processor, so this load word instruction is executed on the processor. Okay. So, and then in order to access the data referenced by this address, then actually this virtual address need to be translated into the physical address, because actually we need to know the real address of the physical memory. So this virtual address need to be translated into the physical address. So this is the address. So it's a virtual address. So, and then page size is the 4 kilobyte. So which means that the size of a page offset field is the 12 bit, as shown in this example. Why? Because the page size is a 4 kilobyte. So which means that this data chunk, 4 kilobyte of data chunk of the virtual memory space is translating the 4 kilobyte of the data chunk in physical memory space. So in this example, so this is the hexadecimal number. So these 3 digits of the hexadecimal number represent the page offset. Why? So this is not translated. This is just copied to the page offset of the physical address. But the upper part, so in this example, 10 need to be translated into the physical address. So this part is called the physical page number. In abbreviation is called the PPN, physical page number. And then the upper part of this virtual address is called the virtual page number. It's called the BPN. Okay, so this BPN is translated into the physical page number. So, and then I said this physical page table. So this is the physical page. This table is called the page table. Okay, and then actually this page table is managed by operating system, and then this is the software mapping table. So this is the software data structure. So which means this page table is located on the memory. Okay, because this is the software data structure, like this one. So, and then when the process is launched on a computer system, then this page table is generated by operating system, and then the address of this page table is stored in the page table register. Okay. So, and then let us assume that this load word instruction is executed. And then, as I mentioned, this is the virtual address. So this virtual address needs to be translated. So the last 3 digits of this address is the page offset. So it is not translated. And so in this example, 10 is the virtual page number. This is the 10. Okay. So in order to get the physical page number, PPN of this address, then we need to access the page table in the main memory. Okay. So in order to access the page table, we need to know the address, the first address of this page table. So base address, which means the base address of the page table. So page table looks like this one, like M. So, and then this array. So this is the array, and then this array is indexed by virtual virtual page number. Okay, so the start point, the pointer of this page table is stored in the page table register. And then when this load one instruction is executed, then we can get the virtual page number 10. So this then processor access the page table using this virtual page number. So in this example, the virtual page number is the 10. So which means that we access the page table using the 0x10. Okay, this becomes the index of the page table array. Okay, page table entries. So which means using the 10, the processor access the page table entries, then we can get the physical page number stored in the target entry of the page table. Okay, so and also the entry should be valid. So which means that this page is located on physical memory. So which means we can get the physical page number. So let us assume that this physical page number is the 0x01. Okay, so we access the page table. Let us assume that this page table array is the PT. Okay, then we access this page table using the virtual page number, and then we can get the physical page number 0x01. Then the physical page number becomes the 0x01, and then page offset is just copied to the page offset of the physical address, so it becomes the 004. So which means that the physical address becomes the 0x01004 in this example. Okay, that's how the virtual address is translated into the physical address. And then, so actually, in order to access the real data, then we need to know physical address, not virtual address. So as I mentioned, the virtual means fake. It's just a virtual. So when a processor access the virtual memory space, so which means this memory space is a fake space, and then we just access this fake memory space using the virtual address, fake address. So in order to access the real data, then this fake address need to be translated into the physical address. Okay, so we need to get the physical address. Then that's how this example shows how to translate the virtual address to physical address. So which means that virtual page number VPN is translated into the physical page number. So page offset is just copied. So we can get the physical address 0x01004. And then using this physical address, we can access the RAM. Okay. So DRAM, so which means that it's a real main memory. Okay. Then that's how the virtual address is translating the physical address. So, and then as I mentioned, this is called the page table. And then as I mentioned, page table is the software structure. So, but if the requested virtual address, so which means that this page, the request page can be found on the physical memory, or the request page cannot be found on the the real physical memory. So which means that the data is on storage system. So in this case, this valid bit is 0. And then this situation is called the page fault. Okay, so it's similar to the cache miss, right? So when the load instruction is executed, then we first check the cache, right? And then there are two cases: the data can be found in the cache, or data is not found in the cache, right? And it's the same to the virtual memory system. So when the load instruction is executed, then actually this process requests the data using virtual address, which means that this page can be found in the physical memory, or the page is not found in the physical memory. So which means when the page table is accessed for this translation, if the valid bit is 0, so which means that this page is not on the physical memory, right? So why do you need this physical page number? In order to generate the physical address, and then we use physical address to access the RAM, the physical memory. And if the page is not found on the DRAM, which means that this PPN is not valid, it's invalid. So if the valid bit of the page table entry is 0, which means that the request page is not on the memory. And then this situation is called the page fault. Okay, so what should we do? The page is not present in the main memory, then we need to transfer this data to we need to read the requested page on the disk, like storage system. And so the page on the disk is transferred to the physical memory, okay, physical memory. So which means that if this page is transferred to the physical memory, then it becomes the valid, and then we can get the physical page number. So after that, we can get the physical page number for this virtual page number, and then we can get the physical address. And then this process, so the required process for page fault situation is called page fault handling. Okay, so what is required? The page is transferred from disk to the physical memory, so to RAM, and then after that we can get the new PPN. Then using this PPN, we can get the PA, the physical address. Then using this physical address, we can access the physical memory. But we learned that the storage, the disk is very, very slow, right? So which means in order to read a page from a disk, then it will take a very long time. So actually the page fault is handled by operating system also. And the page fault is the kind of exception. So which means when the page fault is detected, then exception is raised, and then the exception is handled by operating system. And then required operation is the same to what I explained. The page is read from the disk, and then this page is transferred to the memory, and then the PPN is updated to the page table. And then using this updated page table, we can get the page address. And then using this page address, we can access the physical memory. So it will take a very long time. So this is the kind of exception. And then this page fault is handled by page fault handler. Okay. So that's how the page table is used for virtual address translation into physical address. Okay. So virtual page number is translated using the physical page number by page table. And then, but we can also find the invalid entries in a page table. Okay. Then, how can we manage the these multiple pages on the page table? So we can say I said that the main purpose of the virtual memory system is to use this physical memory space like a cache. So which means that in this cache is a physical memory space, then we need to store the frequently accessed data, right? So which means we need to also manage the replacement, page replacement. Okay. So when you learned about the cache blocks can be also replaced. And then we can use the LRU replacement policy. So which means least recently used cache block is evicted from the cache. So which means because in a virtual memory system, we just use this physical memory like a cache, then which means when the page is replaced, then we can also apply we also employ LRU replacement policy, right? So which means the page fault is detected, then the old page can be evicted from this physical memory. Then how can we select the evicted page? We can apply the LRU replacement policy like a cache, right? But as I mentioned, the physical memory size is very large, so it's not easy. It's not easy to manage the history, the access history of this all page tables, right? So actually, we used some simplified replacement policy. So actually, so in each page table entry, then the operating system use the reference bit. Actually, its reference bit is called the use bit. So which means that if a page is used, then the PT, this reference bit of a corresponding PTE is set to 1. Okay, so which means that the page table entry is accessed, and then this reference bit is periodically cleared to 0 by operating system. So which means that it's cleared by 0 by operating system, all cleared. But then if a page is accessed, then the used page is the reference bit of the used page is set to 1, and then if the replacement is required, then the page if the reference bit of the page is 0, then this page is selected. So this is the simplified way to apply the some LRU-like policy. Okay. But what is the issue of this page table access? So, as I mentioned, the page table, this page table is its software data structure. Okay. And then it means this data structure it looks like the PT and then arrays, the entries. So actually, in order to access the page table, then we need to access the main memory, right? The page table is the software structure, right? It looks like a PT, and then this entry of the PT is indexed by virtual page number. Because this is the software structure, this page table is located on memory. Now what's the problem? Let of the load word is executed by a processor. And then in order to access the real data, then this virtual address needs to be translated into the physical address. Which means we need to access the page table which is on main memory. So which means for every virtual address to physical address translation, we need to access main memory. What's the problem? Main memory is very, very slow. Now, in order to support the virtual memory concept, then for every load instruction, well, every store instruction, every memory transfer instruction, then we need to translate the virtual address to physical address, but it requires access to main memory. So which means that it requires the access to page table, which is on main memory. But that's ridiculous. Why? When the load word is executed in order to translate the virtual address into physical address, then we need to access the main memory. Well, then why do you use cache? We have cache hierarchy to reduce the accesses to main memory, because main memory is very, very slow. But in order for this translation, virtual address, the translation of a virtual address into physical address, then we need to access main memory. It's ridiculous, right? Then how can we avoid this long memory latency for accessing physical table? The problem is that for virtual address to physical address translation, we need to access page table in main memory, the physical memory, but main memory is very, very slow. How can we solve this issue? Also, we can handle this issue also like a cache. So what does that mean? So for this virtual address to physical address translation, which information is required? We require virtual page number to physical page number mapping information, right? And then we know that when the virtual page number is translated into the physical page number, and then the page size is the 4 kilobyte. So which means that actually this translation is required for 4 kilobyte of data chunk. Okay, it's a 4 kilobyte. And then when we do in the first class of the memory hierarchy chapter, then we learned the data in our application exhibit locality. So what does that mean? The load word A, load word B, load word C is executed in the same application, and then actually because of the spatial locality, then with a high probability these data A, B, C can be found in the same page, right? Because the page size is the 4 kilobyte, it's very large. And then when the data are requested by the same application, then with the high probability, this data can be found in the same page, right? Because of the spatial locality. So what does that mean? When this data is these addresses, the ABC addresses ABC are translated into the physical address, then we can apply the same BPN to PPN mapping information. So same, which means if a certain page table entry is used for this virtual address to physical address translation, and then in the near future, the same page entry will be accessed again and again. So we can also apply the cache-like structure, okay? Because if we once this virtual page number to physical page number mapping information is used, then with a very high probability, this information will be used again and again and again, repeatedly. So we can just cache this mapping information in the dedicated hardware structure. Okay, so which means that if a processor has the cache for page table entry, then we can access this page, the target page table entry, very quickly. And then this structure is called the TLB. So TLB means the translation look aside buffer. So it's a TLB. Okay. So TLB means that when the page table entry is requested by for virtual address to page physical address translation, then this page table entry is cached in the TLB, so translation local side buffer. And then after that, when this same page table entry is requested, then this page table entry can be found in the TLB with very high probability. So TLB miss rate is very, very low, okay, because of the low quality of data access, our application, our data, okay. So not support the fast translation, the processor also includes the cache of the page table. It's called the TLB. Okay. So this is the structure of the TLB. Okay. So I said that TLB is the cache of page table. Okay. So which means let us assume that load word. So the load word is executed. So which means that this is the address A. Then in order to translate this virtual address into the physical address, then we need to access the page table, right? But because the processor has the TLB, that is the cache of the page table, then for this translation, the processor first access the TLB and then check if the virtual page number is found in the TLB. So TLB is a cache. So the TLB is referenced by virtual page number. So which means that the page TLB has also the many entries and then the like a virtual page number. So this is the virtual page number. And then as I mentioned, the TLB is referenced by virtual page number. Okay. So we can use the part of the virtual page number, this raw part of the virtual page number as the index, like a cache. So index of the TLB, and then the upper part of the virtual page number as the tag of the TLB. Okay. So this address is translated into the physical address, then firstly the TLB is checked. And then if this mapping information is found on TLB, so which means that we need to also check the tag, and then also we can access the target entry of the TLB using the index of this virtual page number. Okay. Then if this tag is matched, is the tag of this virtual page number, then is the hit case. It's the same to the cache hit. So if the tag is matched, then which means that this, and then if also this is bit is valid, so which means that TLB has the requested mapping information. Okay. So what is the mapping information? It's the physical page number, right? So in this case, in the TLB hit case, this physical page number is returned. So using this physical page number, the virtual address can be translated into physical address very quickly. Right. Is this similar to the cache hit case? But if the TLB miss is encountered, so which means that in the target entry, if the target entry is invalid, or if tag is not matched, then this means this is the TLB miss case. Right. So what should we do? So which means that TLB does not include the requested mapping information. So which means we need to access the page table. Okay. Then if the page table has the valid mapping information right here, then this ppn is given to the TLB, and then this information is allocated in the TLB entry. Okay, and then this ppn is also provided to the processor, and then this virtual address ppn is translated into ppn, the physical page number. Okay, so TLB is just a cache of the page table entries. Okay, so this is very good idea, right? So as I mentioned, when the pages are, the virtual address is translated the physical address, then but this translation is done by a page granularity, and the page size is usually 4 kilobyte. So which means that we can observe very high locality for this page table entry accesses. So if once the page mapping information is used, then this mapping information, the virtual page number to physical page number mapping, can be cached in the TLB, and then if this mapping information is cached in TLB, then in the next time we can find this mapping information in the TLB with high probability. It's a TLB idea. So modern processor also supports the TLB, okay, for this fast translation. Okay. So if the so I explained about the TLB hit case and then TLB miss cases, and then so for the TLB miss, then the page table is also accessed, and then if the page the target page is invalid, so it is in this case is the page fault, right? Then we need to access the disk. Okay, and the disk is very slow. So as I mentioned, the page is not in memory. This is the page fault. Then operating system needs to handle this case. This is the kind of exception. Okay, so this is the page fault handler. Then how can we access cache? So actually, so in the first thing, so this is the processor, and then when the load instruction is executed, then I explained that we need to first access the cache, and then if the cache miss is encountered, then we access the main memory. Then which address is used for accessing cache? So actually, this main memory is the real memory. And then the cache hierarchy, when the cache is accessed, then actually we just store the real data. Since that the address mapped to this data in the cache is should be physical address. Okay, so what does that mean? The processor access the cache, then processor need to access cache using physical address, right? So, and then what's the problem? The load word A is executed, and this A is the virtual address. Then in order to access cache, then this A need to be translated into the physical address. Right. So which means in order to access cache, then we need to first check the TLB. Right. In order to translate the virtual address into the physical address. So which means that when the load word A is executed, then this A need using this address, then we need to access the TLB first, then we can get the physical address. Then using this physical address, we need to access the Aaron cache. What's the problem? The problem is that, TLB is another memory structure, so it has also latency. So which means that we need to consume some cycles for accessing TLB. Then after that, we can access the Aaron cache. So which means, so we actually originally actually in the previous class we assumed that for the cache hit, then this cache hit time is just 1 clock. But for this scenario, then we first need to access the TLB, so it will consume 1 clock, and then we get the physical address, and then we need to access the Aaron cache. So which means that we require additional cycles for accessing TLB and the virtual address to physical address translation. Why do you use cache? Okay, why do you use cache? And what is the main purpose of the Aaron cache? So actually, when you design a cache, then we need to reduce the hit time. But because of this TLB accesses, then hit time need to be increased. We require additional cycles for accessing TLB. Okay, so that's also the significant performance issues of the virtual address system. Right? So this figure shows how the caches are really accessed. So first, the load access the cache using this virtual address. Then the first we need to access the TLB. So this is and then we can get the physical address. So actually the page offset is just copied to the page offset field of the physical address. Then we need to use the PPN. And then using this physical address, then we need to access the cache. So cache. Okay. So actually, then we need to access the cache using physical address. Okay, like this process. But because of the performance issue, then Aaron cache can be accessed by virtual address. Okay, so in order to reduce the latency for accessing Aaron cache, but the L2 cache, so actually we can hide the latency of the TLB when you access the L2 cache. So L2 cache is usually accessed by physical address, but Aaron cache So if we use access the Aeron cache using this physical address, then we firstly need to access the TLB. So in this case, the latency to Aeron cache is increased. So some systems, some CPU access the Aeron cache using virtual address. Okay. So this is some issues of the virtual memory systems. But most of the processors supports the virtual address. Okay. So and then actually there are many benefits for using virtual address. So actually the software that we can provide the large virtual memory space. So it's a fake, even though it's a fake memory space. But when we write the code, we don't need to consider about the memory management issues. So memory spaces are actually managed by operating system using page table. Okay, so virtual memory concept has many benefits. Even though recently we used a very large DRAM, virtual memory space has also many benefits. Okay, that's why we use the virtual memory. Okay, so this is the end of this chapter 5. So in chapter 5 we learned about the memory hierarchy. So and then also we learned about the cache. So the cache is a critical component, because without cache, then we need to access main memory directly, but main memory is very slow. That's why we use cache. Also, when we discuss about the performance of a cache, then we learn that with the cache, then we can reduce the effective CPI. So which means that we can increase the performance. Also, the cache exploits the locality of our application. And we also learned about the virtual memory. And so we learned that, so actually the software access the virtual memory space using the virtual address. So in order to access the real physical memory, then we need this virtual address need to be translated into the physical address, right? And then in order to support this translation, the operating system create the physical table. Okay, and then also in order to support the fast translation, the hardware supports the cache of the page table. It's called the TLB. Okay, so this is the end of the chapter 5. Okay, so actually, as I mentioned, the virtual memory concept is a little bit tricky, because so we are just handling the virtual space. It's a fake space. Okay, it's not real, but in our computer system, so it's a kind of abstraction. So it means to the software side, we do not reveal some difficult concept of the memory management. It's just hidden by operating system. The software just handles the very large virtual memory space without any limitation. But the difficult part, like the hardware resource management, and then some data protection, and then also the memory space management are handled by operating system and hardware. Okay, so I hope you can understand this virtual memory concept. Then this is the end of the chapter 5. Okay, so the chapter 5 is the very important chapter of this course, because the memory hierarchy, the memory system is also critical for the performance of entire computer systems. Okay, so I hope you can also understand the important topics on this memory hierarchy and then virtual memory. Okay, so I will stop here. Then I hope the lectures are properly recorded. Again, I hope this lecture you can also understand the important concept of the memory system of computer system. Okay, so thank you for your attention, and then see you in the in-person class, the last class of the discourse on Tuesday, right? Okay, thank you for your attention, and then see you in the next class.